So now let us begin off with the theory of gravitation. So my topic is gravitation. Okay, now first let us begin off with Kepler's law of planetary motion. Now the Kepler's first law states that all planets, they move around the sun in elliptical orbits with the sun at the focus of the orbit. Okay, so let's say this is my orbit. Okay, so the planets are going to revolve around the sun in this elliptical path, and the sun is going to stay at the focus of the ellipse. Okay, so this is my Kepler's first law. Fine. Kepler's second law states that the position vector from the sun to the planet sweeps out equal area in equal interval of time, which implies that if my planet swipes out this area, let's say A1, in time delta T1, the planet is going to swipe the same area A1 in time delta T1. Okay, again, fine. So at each equal interval of time, the planet is going to sweep out equal area. Okay, this was my Kepler's second law. Okay, now this, in other words, can also be said that the aerial velocity of the planet around the sun always remains constant. So if I write it down in words, I'll write down aerial velocity of a planet remains constant around the sun. Okay, fine. The Kepler's third law states that the square of the time period of the planet around the sun is proportional to the cube of the semi-major axis of the ellipse, or the mean distance of the planet from the sun. So like this is my elliptical path. Fine. The semi-major axis is, let's say, of length A. Fine. So the time period of revolution of the planet around the sun is, let's say, T. According to Kepler's third law, the square of this time period is going to be proportional to the cube of this semi-major axis. Okay, fine. Now let us move on to the next topic in gravitation, that is Newton's law of gravitation. The Newton's law of gravitation states that if there are two masses m1 and m2, m1 and m2, separated by a distance of, let's say, r, there is going to exist a force of attraction between these two particles by virtue of their masses. The forces are going to be attractive in nature, that is, m1 is going to be attracted towards m2 and m2 is going to be attracted towards m1. Basically they would be action-reaction pairs. Fine. So I'll write it down as F12, and this can be written as F21. Vectorally I'll write down F12 vector is negative of F21 vector. Okay, fine. Now this gravitational force is proportional to the product of the two masses. Okay, and it is inversely proportional to the square of the distance between the two masses. Fine. So mathematically I'll write down F mod of F12 vector equals mod of F21 vector is proportional to m1 into m2 upon r square. Now if I remove this proportionality sign from this expression, I'll have to involve a constant. This constant is going to be my universal gravitational constant, which is denoted as G. So I'll write down mod of F12 equals mod of F21 equals G into m1 into m2 upon r square. Fine. So this is going to be my magnitude of the gravitational force of attraction between the two masses. So this is basically my Newton's law of gravitation. Fine. Moving on to the next topic in the topic of gravitation. The next topic is gravity and acceleration due to gravity. Okay. So fine. Now, the Earth attracts all the bodies towards itself. Okay. So let's say I have a body which is at a distance of r from the center of the Earth. If the mass of the Earth is, let's say, ma, the force of attraction, the gravitational force of attraction which this particle is going to experience due to the Earth is going to be written as G into me into m upon r square. Okay, this was the Newton's law of gravitation. Fine. Now, on the surface of the Earth, the value of r becomes equal to ra if ra is the radius of the Earth. Okay, so on the surface of the Earth, on the surface of the Earth, r equals ra. Okay, and if let's say f becomes equal to G into me into m upon r square. Okay, fine. So this is the force of gravitation on the surface of the Earth on this particle of mass small m. Fine. Now this force of attraction, that is the gravitational force of attraction, is going to produce some acceleration. Okay. Now this force can also be written as the mass of this body of this body into the acceleration which we presently say as the acceleration due to gravity. Okay, this acceleration due to gravity is for the bodies which are near to the surface of the Earth. Okay, fine. So we obtain the value of G. I mean, if I put in the value of F as G into me into m upon r square, we obtain the value of small g, that is the acceleration due to gravity, as G into me upon r square. So this is basically the acceleration due to gravity on the surface of the Earth. Now this acceleration due to gravity is actually going to be affected by various factors. Okay, one of these factors is effect of altitude. The other factor which we need to consider is the effect of depth, and the third factor which we need to consider is the effect of latitude. Okay, so basically what I want to say is that if I increase the height of my body from the surface of the Earth, the gravitational force is actually going to decrease. Like if I move my body from this point to this point, definitely the gravitational acceleration due to gravity would be lesser at this particular point than on the surface of the Earth. That is, this happens because the magnitude of the gravitational pull actually decreases as we increase the distance of my body from the center of the Earth. Okay, so let's say for a time being that my body is taken to a height of h from the surface of the earth, and the mass of the earth is me and re is the radius of the earth. Okay, so let's say at this particular point the acceleration due to gravity is g dash, and at the surface of the earth the acceleration due to gravity is g. I'm not deriving out the expression, it is pretty simple. We just need to use the expression F equals, if I say that the force of attraction between the earth and the body of mass m at this particular point is F1, so F1 is going to be equal to g into me into m upon re plus h square, and F on the surface of the earth, let's say, is Fs, is going to be equal to g into me into m upon re square. Okay, this is going to be equal to m into g dash, and this is going to be equal to m into g. Okay, fine. So if I divide these two expressions, I'll get re square upon re plus h square equals g dash upon g. Okay, so from where we get the expression of g dash as g into re square upon re plus h square. Okay, so this is my expression of the acceleration due to gravity of a body which is at a height h from the surface of the earth. Okay, now if the body is very close to the surface of the earth, that is when h is much less than re, in that case I can binomially expand this particular expression and I'll obtain the value of g dash as g into 1 minus 2h upon re. Okay, so this is going to be my acceleration due to gravity. Okay, for a body which is close to the surface of the earth but which is not at the surface of the earth. Fine. Okay, so this was the case of effect of altitude. Fine. Now let us talk about the effect of depth. Fine. So if I have my body, this is my earth. Okay, it's of mass me and it has radius re. Okay, and my body is at a depth of h from the surface of the earth. Fine. So let's say at this particular point the acceleration due to gravity is g dash, and on the surface of the earth the acceleration of due to gravity was equal to g. I'll obtain the relationship between g dash and g as this. So this is something which we need to remember simply. Okay, so we see that with the depth, with increasing depth, my acceleration due to gravity actually decreases. It becomes equal to 0 at the center of the earth. So this is one result which we should remember. Okay, effect of altitude, effect of latitude, that is my third effect. So if I talk about the effect of latitude, let's say I have my earth which is revolving, which is rotating with an angular velocity of omega, and I have my body at a latitude of, let's say, lambda. Okay, fine. The magnitude of acceleration due to gravity at this particular point, let's say, is g dash. Okay, and g is the acceleration due to gravity of the earth, considering that it is not rotating. Okay, that is g G is G into ME upon R square. Okay, fine. So if we try to relate G dash to G in this particular case, I'll get G dash as G minus omega square into RE into cos square lambda. Okay, so this is another expression which we need to remember. Okay, so there are a few cases which can come up from this expression. That is, my first case would be when my particle is at the pole. Okay, in that case lambda will be equal to 90 degree and cos square lambda will be equal to 0. So at poles my G dash is equal to G. Okay, so we get normal values of acceleration due to gravity. Okay, so at poles the body is going to experience the acceleration due to gravity as if the earth was completely stationary, as if the earth wasn't rotating at all. So this is my case of poles. At poles when lambda equals 90 degree. At the equator the acceleration due to gravity is going to reduce the most. Okay, the effect of rotation is going to be observed maximum at the equator. Okay, where lambda is equal to 0. So at the equator G dash is equal to G minus omega square RE, where lambda is equal to 0, and this is the case at equator. Fine. So these are the few cases which we need to remember. Okay, let us talk about gravitational fields. Now if I have a body which is of mass m and the gravitational field is at a point R from this body is going to be defined as G into m upon R square. Okay, now this gravitational field is actually going to be directed towards the body. Okay, this gravitational field in words is actually defined as the force experienced by a unit mass at a distance of r from another body. Okay, so this is my another body and this is my unit mass. Okay, so this is actually the force experienced by this unit mass. Okay, so if I bring in a body of mass, let's say m1, at this particular point the force which this body of mass m1 is going to experience is going to be written as F equals E into m1, that is G into m into m1 upon r square, which is nothing else but Newton's law of gravitation. Okay, fine. So this was all about gravitational field. If I talk about the gravitational field on the surface of the earth, so this is my earth of mass me and its radius is re. The gravitational field E, and at the surface of the earth is going to be written as G into me upon re square. Okay, and at a distance of r from the center of the earth, the gravitational field is going to be written as G into me upon r square. Okay, fine. Now let us talk about gravitational potential energy. The gravitational potential energy is basically defined as the work done in bringing a body from infinity to a particular point in presence of another body. So let's say this is my another body of mass m. Okay, and I have a body which is of mass m1, which is initially at infinity, and it is brought from infinity to a point which is at a distance of r from this body of mass m. Okay, so gravitational potential energy is basically going to be defined as the work which this force of gravity does to bring this particle of mass m1 from infinity till this point. Okay, so the gravitational potential energy actually turns out to be minus g into m into m1 upon r. Okay, fine. Gravitational potential is going to be the work done by this body on a unit mass. So gravitational potential at this particular point is going to be written as V is going to be equal to potential energy at this particular point upon m1, that is the potential energy for a unit mass. This turns out to be minus g into m upon r. Okay, fine. Now let us talk about a relationship between gravitational field and potential. Okay, sorry. Fine. So if let's say my potential is of form V, X, Y, Z, and my gravitational field is of form, let's say, Ex I cap plus Ey j cap plus Ez k cap. So Ex is going to be equal to del upon del x of V x y z. Ey is going to be the partial derivative of V with respect to y, and Ez is going to be the partial derivative of V with respect to z. Okay, fine. Okay, so this is the relationship between the potential, gravitational potential, and the gravitational field. Okay, now let us talk about satellites. Okay, so basically the celestial bodies which revolve around the planets in close and stable orbits, they are called satellites. So the satellites can be natural as well as artificial. The artificial satellites are basically those satellites which are man-made, which are actually ejected from the, which are actually launched from the Earth in a particular trajectory, so as they reach a particular orbit and they start revolving around the Earth. So those satellites are actually man-made satellites. Okay, let us talk about the orbital speed of a satellite, which is at a height h from the surface of the Earth. So let's say this is my Earth. It's of mass me and it has got radius re, and I have my satellite which is at a height of h from the surface of the Earth, and it is revolving around the Earth at a radius of r plus h. Okay, so the radius of this orbit is r plus h. Okay, fine. So the orbital velocity for this thing to happen, let's say, is v naught. Okay, so v naught, I mean, what I just need to do is I just need to equate the centripetal force, that is m v naught. Let's say the satellite has mass m v naught square upon r. This is the centripetal force. This actually is being provided by the gravitational force of attraction between the Earth and the mass, so that is equal to G into ME into M upon R square. So this gives me V naught as root over G into ME upon R. Fine. So if I put in the value of R as RE plus H, this gives me the value of V naught as GME upon RE plus H. Okay, fine. In terms of G, where G is GME upon RE square, I'll get V naught as RE into root over G upon RE plus H. Okay, so this is going to be the orbital speed of a satellite which is at a height of h from the surface of the Earth. Now if I talk about the time period of this satellite, T is going to be the circumference of its orbital path, that is 2 pi r upon the velocity, orbital velocity, that is V naught. If I put in the value of r as RE plus H and V naught as this, I'll get the expression of T as 2 pi root over RE plus H whole cube upon G RE square. Okay, fine. Now let us talk about the energy of a satellite which is revolving close to the surface of the Earth. So that energy basically is going to be the sum of the potential energy and the kinetic energy. Okay, the energy actually turns out to be minus G into ME into M upon 2RE. Okay, where M is the mass of the satellite which is orbiting very close to the surface of the Earth. Okay, fine. Let us now talk about the escape velocity. The escape velocity is actually the velocity which a particle requires in order to reach the infinity. Okay, in order to escape the gravitational attraction of the Earth. Okay, so at infinity, the velocity, the final velocity of the body is going to be equal to 0. The potential energy of the body is going to be equal to 0, which implies that the total energy of the body at infinity is going to be equal to 0. Fine. On the surface of the Earth, the body had some potential energy and some kinetic energy. When it was projected with a velocity of v, it had a kinetic energy of half m into v square. Now since we are talking about the escape velocity, this body has been projected with the escape velocity so that it reaches infinity and its final energy is equal to 0. This was my initial kinetic energy. Okay, kinetic energy final is equal to 0. The potential energy final is equal to 0. The potential energy initial is going to be equal to minus G into ME into M upon RE. Now this total process is happening under the influence of a conservative force, which implies that the total mechanical energy is going to be conserved, which implies that KEI plus UI must be equal to KEF plus UF. This implies the escape velocity is going to be equal to 2G into ME upon RE. Okay, so if I put in the value of G, ME and RE, which are actually known values, I'll get my value of VE as 11.2 kilometers per second. Okay, so this is the velocity with which a body needs to be projected in such that it reaches a infinity. Okay, it escapes the Earth's gravitational pull and it reaches infinity. Fine. Let us now begin off with few problems on the topic of gravitation. So this is my first problem. Okay, a small body starts falling onto the sun from a distance equal to the radius of the Earth's orbit. The initial velocity of the body is equal to 0 in the heliocentric reference frame. Find how long the body will be falling. Fine. So in this problem I have sun. This is my sun. It has got its own radius, that is rs, and a body started falling on to the sun from a distance equal to the radius of the Earth's orbit. So this is, let's say, r, where r is the radius of the Earth's orbit. Fine. Okay, I need to find out the time duration for which the body will be falling. Okay, fine. So let's say at any instance of time the body is at a distance of x from the surface of the sun. The acceleration due to gravity of the sun is going to be given by let me write it as omega. It will be given by omega equals minus g into mass of the sun upon rs plus x square, right? Fine. Now this omega can also be written as v dv upon dx, right? This can be written as v dv upon dx. Okay, fine. So this can further be written as v dv equals minus g ms upon rs plus x square into dx. Fine. Now if I integrate this expression, okay, from r till x, and this should be from 0 to v, where v is the velocity of this particle at this particular point. Okay, fine. So I'll get my expression as v square by 2 equals gms into 1 plus rs plus x r from r to x. Okay, sorry, this should be smaller. Okay, so this gives me v square by 2 as g ms into 1 by rs plus x minus 1 by rs plus r. Okay, so this gives me v square by 2 as g ms into r minus x upon rs plus x into rs plus r. Okay, sorry, this should be smaller, and here too. Okay, fine. So this can be written as, v can be written as root over 2g ms into 1 by rs plus x minus 1 by rs plus r. Okay, fine. Now v can be written as minus dx by dt. Okay, in this case x is decreasing as v is increasing, so v can be written as minus dx by dt. Okay, fine. So on solving this equation, I'll write from minus small r to 0 dx equals from 0 to t, where t is the time interval for which this particle travels in midair, 1 by rs plus x minus 1 by rs plus r. Okay, so I just need to solve this expression. I just need to bring this term to LHS and I just need to integrate. On integration, I'll get my value of t as 65 days. Okay, I'm not solving this expression. I expect you people to solve it. Okay, the answer is 65 days, provided my mass of the sun has been given to me as 1.97 into 10 to the power 30 kgs, and the radius of the sun has been given to me as 6.95 into 10 to the power 8 meters, and the radius of the earth is known to us as 6400 kilometer. Okay, fine. So this is going to be the time during which for which this particle is going to be in midair. Okay, let us now move on to the next problem. A double star is a system of two stars moving around the center of inertia of a system due to gravitation. Find the distance between the components of the double star if its total mass equals m and the period of revolution is equal to t. Fine. So a double star would definitely consist of two stars. Okay, so let's say this is my first star, let's say this is my second star. Its mass, let's say, is m1 and the mass of the second star is m2. The total mass of the system has been given to me as capital M, so I'll write down m1 plus m2 equals capital M. Okay, now these two stars, in case of a double star, they revolve around the center of inertia of the system. So let's say this is the center of inertia of the system. Okay, they are going to revolve around the center center of inertia of the system. Okay, fine. So the center of inertia of the system is going to be the center of both these trajectories. Okay, now let's say the radius of this trajectory is r2 and the radius of this trajectory is r1. Okay, so I'll write down r1 plus r2 equals r0, and this is something which I need to find out. I basically need to find out the distance between the components of the double star, which means that I need to find out the distance between m1 and m2. Okay, now these two stars are definitely going to have the same angular velocity. Okay, because they are going to revolve around the center of inertia. The center of inertia basically is always going to lie in between the line joining m1 and m2. Okay, which implies that the line joining m1 and m2 is going to have a constant angular velocity. Okay, fine, which will be equal to the angular velocity of the stars m1 and m2. Okay, fine. Now if I define the coordinate system, okay, with the center of inertia as my origin, I'll write down RC equals minus m1 r1 plus m2 r2 upon m1 plus m2. Okay, now since I've defined my origin at the center of inertia, RC is going to be effectively equal to 0. Okay, fine. So this gives me one relation between m1 r1 m2 r2 as m1 r1 equals m2 r2. Okay, so this is, let's say, my first relation. Okay, fine. Now if I use these two expressions, I'll get my value of r1 as m1 r0 upon m1 plus m2. Okay, and r2 as m2 r0 upon m1 plus m2. Okay, fine. Now I know that the angular velocity is going to be the same. The stars are going to revolve around the center of inertia under the impact of a centripetal force, which is going to be the gravitational force of attraction between the two stars. Okay, now the gravitational force of attraction between the two stars is going to be equal to G m1 m2 upon r0 square equals, this must be equal to m2 r2 into omega square. This must also be equal to m1 r1 into omega square. Okay, fine. Now if I put in the value of r2 as this and r1 as this in this expression, okay, I can write it down as m2 square into r0 into omega square upon m1 plus m2. This must also be equal to m1 square r0 into omega square upon, sorry, I made a mistake. This must be r2. Okay, this must be m2. Okay, I mean, if I use these two expressions, I'll get r1 as m2 into r0 upon m1 plus m2 and r2 as m1 r0 upon m1 plus m2. Okay, now if I put in this expression, I mean, if I put in this values of r1 and r2 in this expression, I'll get m2 m1 omega square upon m1 plus m2 on both the sides. Okay, fine. Now the time period has been, let's say, given to me as t. So omega is going to be equal to 2 pi by t, where t is the time period of the revolution. Okay, now if I take on these two values, I'll write down G m1 m2 upon r0 square must be equal to m1 m2 into omega square upon m1 plus m2. Okay, I get m1 into m2 cancelled on both the sides. Fine. And if I put in the value of omega as 2 pi by t, I'll get my expression of r0 as gm into t by 2 pi square to the power 1 by 3. Okay. Fine. Sorry, there must be r0 actually. So there would be r0 here, from where I get the value of r0 as this. Okay, fine. Let us now begin off with the next problem in the topic of gravitation. A uniform sphere has a mass of capital M and radius r. Find the pressure P inside the sphere caused by gravitational compression as a function of distance r from its center. Evaluate P at the center of the earth, assuming it to be a uniform sphere. Okay, so in this problem I have a uniform sphere which is of radius capital R and mass capital M. Okay, I need to find out the pressure caused by the gravitational compression at a distance of r from the center of the sphere. The pressure is going to be the same throughout this particular shell. Okay, which is of radius smaller. Okay, now let us consider a infinitesimally thin shell of radius x. Okay, let's say its thickness is dx. Okay, let's say its thickness is dx. Okay, its mass, let's say, is dm, which is going to be given by 4 pi x square into rho into dx. Okay, this is going to be the mass of the shell. Fine. Okay, now the gravitational field at any point on this shell is going to be g vector given by minus 4 pi by 3 into g into rho into x vector. Okay, now g is going to be directed inwards. That is why I have taken up this minus sign. Okay, I have just represented it in a vectorial form. In the process of calculation of pressure, we are not going to consider any signs. Okay, pressure is basically a scalar quantity, so I just need to find out the magnitude of the pressure. Okay, fine. So this is the gravitational field. The whole sphere is going to experience a force because of this. The whole shell is going to experience a force because of this gravitational field. Okay, that force, let's say, is df. Okay, it is going to be directed inwards, so its magnitude is 4 pi by 3 into g into rho into x into dm. Okay, that is the mass of the shell. Okay, basically F is equals to gravitational field into the mass. Okay, so that is what I am doing here, into dm. Dm can be written as 4 pi x square into rho into dx. Okay, so this is the small force df which the shell experiences because of the sphere which is present inside the shell. Okay, now this shell is going to experience a small pressure which is going to be given by df upon a. Okay, which is going to be given as 4 by 3 pi into g into rho into x into 4 pi x square into rho dx. That is the force, small force upon area of the shell, that is 4 pi x squared. It gets cancelled on both the sides. So if I want to find out the total pressure at a distance of small r from the center of the sphere, I'm basically going to integrate it. This integral is going to be from 0 to p. This integral is going to be from small r till capital R. Okay, fine. So this gives me p as integral of small r to capital R 4 by 3 pi into g into r into rho square into x dx. Okay, so p turns out to be 4 by 3 pi g into r into rho square into x square by 2. This is going to be from small r till capital R. So pressure turns out to be 4 by 3 pi r into g into rho square into capital R square minus small r square by 2. Okay. Sorry, I must not be having any r here. Okay, I didn't have any r there in the expression of dp, so I'm not going to have any capital R here, so I just need to eliminate it. Fine. So this is going to be the pressure which is going to exist at a point which is at a distance of small r from the center of the sphere. Now in the second subpart of the question, I had to find out the pressure at the center of the earth, considering it to be a uniform sphere. So in that case, I just need to replace small r by 0. Okay, so on replacing r equals 0, we get the pressure at center of the earth as 4 by 3 pi into g into rho square into capital R square by 2. Okay, so this is going to be the pressure at the center of the earth. Okay, now let us begin off with the next problem in the topic of gravitation, which is this: calculate the proper potential energy of gravitational interaction of matter forming a thin uniform spherical layer of mass m and radius capital R, a uniform sphere of mass m and radius r. Fine. So let us first solve the first problem. Okay, so this is my shell. I need to find out the proper potential energy of gravitational interaction of the matter forming this particular shell. This shell is of radius r and it is of mass m. Okay, now let us consider a small mass dm on this shell. The gravitational potential energy of interaction of this particular mass dm with the whole spherical shell is going to be given by, let's say, du. Okay, now this du is going to be minus g into small m, that is the mass of the shell, into dm, that is the mass of the small particle of infinitesimally small dimensions, okay, upon r. So this is the small potential energy interaction. Okay, so in order to find out the proper potential energy of gravitational interaction, I just need to integrate du. Okay, so if I integrate du, this would be from 0 to u, and this is going to be from 0 to m. Okay, fine. So this gives me the proper potential energy of interaction as minus g into m square by 2r. Okay, so this is going to be the proper potential energy of interaction, okay, of each element with all the other elements. Fine. So this was my first subpart of the question. Now let us move on to the next subpart of the question, where I have a uniform sphere of mass small m and radius r. Okay, now this sphere can be thought of being composed of infinite thin shells. Okay, like if I consider this particular shell of radius x and mass dm, so this whole sphere is made up of these shells, okay, of different radii. Okay, fine. Now let's say that at any instance while the sphere was being formed, its radius was x and a shell of small thickness dx was brought and put on this sphere of radius x. Okay, now the gravitational interaction energy between this shell and this sphere was du equals minus g into, let's say, the mass of this sphere is mx into dm, that is the mass of the shell upon x. Okay, so this is going to be the small potential energy interaction between the shell which is being put on a sphere of radius x. Okay, fine. Actually this term is the potential, gravitational potential due to this sphere x on its surface. Okay, now since this shell of mass dm is being brought on this sphere, this is actually the potential energy interaction. Fine. Okay, now this mx can be written as minus g into mx can be written as the volume of the sphere of radius x into the density of the total sphere into the small mass dm upon x. This is going to be du. Fine. Now dm can be written as 4 pi x square into dx, that is the small volume dv of the shell which is being brought on the surface of this sphere into the density of the sphere. Fine. So du becomes minus g into du becomes minus g into 4/3 pi x square into rho into 4 pi x square dx into rho. Okay, so this is the small potential energy interaction. Okay, in order to find out the total potential energy interaction, I basically need to integrate this du. So this is going to be from 0 to u and this is going to be from 0 to r, where x is varying from 0 to r. Okay, so u turns out to be minus g into 16 pi square rho square upon 3 into r to the power 5 into g by r to the power 5 upon 5. if I solve this integral, I'll get this as my u. Okay, now rho can be replaced as capital M, small m upon, that is the mass of the sphere, upon 4 by 3 pi r cube. Okay, so this is going to be right. Now if I put in the value of rho as this in this expression, I'll get u as minus 3 by 5 g m square upon r. Okay, so this is going to be my proper potential energy interaction of this whole sphere of mass small m and radius r. Okay, let us now move on to the next problem, which is this. An artificial satellite of the moon revolves in a circular orbit whose radius exceeds the radius of the moon eta times. In the process of motion, the satellite experiences a slight resistance due to cosmic dust. Assuming the resistance force to be dependent on the velocity of the satellite as F equals alpha v square, where alpha is the constant, find how long the satellite will stay in the orbit until it falls on the moon's surface. Okay, so this is basically my moon. It is of mass let's say m. Okay, and my satellite is moving in a circular path whose radius exceeds the radius of the moon by eta times. So its radius is eta into r. Okay, now let's say that in this circular path the satellite had a velocity of v1. Okay, now the drag force is definitely going to be opposed to the velocity. So during the motion of the satellite, it will always tend to move in a circular path. Okay, in a circular path of decreasing radius, but it will always tend to move in a circular path. Okay, fine. So which implies that when it strikes the surface of the moon, its velocity is going to be tangential, and still it would be moving in a circular path, and the centripetal force of that circular path is going to be provided by the moon, gravitational attraction of the moon and the satellite. Okay, fine. Now let's say that when it strikes the moon, its velocity is v2, which is definitely going to be tangential to the surface of the moon at which it strikes. Okay, fine. Now let us find out the velocity v1 in terms of eta capital M. Okay, now at this particular instance, the centripetal force which this satellite requires is mv1 square upon eta r. This is going to be equal to the gravitational attraction of the moon and the satellite, which is, so this gives me the value of v1 as root over gm upon eta r. Okay, so this is going to be the velocity of the moon initially. Okay, now let us now find out the velocity of the satellite when it strikes the moon. In that case, the centripetal force required is mv2 square upon r. This must be equal to the gravitational attraction of the moon and the satellite at that particular point. So this gives me v2 as root over gm upon r. Okay, fine. Now I've been said that the resistive force is proportional to, is given as alpha into v square. Okay, now at this particular instance of time, let's say the velocity of the satellite is v. Okay, so the force which acts in the opposite direction on the satellite is given by this relation. Okay, now this force can be written as m into dv upon dt. this is given as alpha into p square. Fine. Okay, so this can be written as m into dv upon v square equals alpha into dt. Okay, so in order to find out the time for which this satellite flies in the air until it strikes the moon, in order to find that out, I basically need to integrate. Okay, so this is going to be from 0 to t, this is going to be from v1 to v2. Okay, so this gives me minus 1 by v, this is going to be from v1 to v2 equals alpha by m into t. Okay, so if I put in the value of v1 as root over gm upon eta into r and v2 as root over gm upon r, I'll get my value of t as m by alpha root over r by gm into root over eta minus 1. Okay, now if I say that the acceleration due to gravity on the surface of the moon is g, so g is going to be given by gm upon r square. So if I substitute if I manipulate this particular expression in terms of g, that is if I multiply r in the numerator and the denominator, I'll get my expression of t in terms of g as m by alpha into root over eta minus 1 upon root over g r. Okay, so this is going to be the time of flight of the satellite. Okay, now let us move on to the next problem, which is this. Distance between the center of two stars is 10 a. The masses of these stars are capital M and 16 capital M, and their radii are a and 2a respectively. A body of mass small m is fired straight from the surface of the largest star towards the smallest star. What should be the minimum initial speed to reach the surface of the smallest star? Obtain the expression in terms of g, m and a. Okay, fine. So in this problem I have two stars. One star is of radius a, the first star is of radius a, this is basically the smallest star, it is of mass capital M, and my largest star is of radius 2a and it is of mass 16m. Okay, fine. The distance between these two stars is 10a. Okay, I need to find out the minimum velocity with which a body is projected from the largest star, from the surface of the largest star, such that it somehow reaches the smallest star. Okay, now there is going to be a point, let's say O, between the two stars where the gravitational field is going to be equal to 0. Okay, so on the left hand side of this particular point, the net force is going to be directed leftwards, and on the RHS of this point the net force is going to be directed towards the right. So if my particle somehow reaches this point, it is definitely going to be pulled in the leftward direction and it will definitely reach the smaller star. So basically it needs to reach this point somehow. By somehow I mean that at this point, if its velocity is equal to 0, is tending towards 0 or is equal to 0, it is going to be pulled towards the left and it will reach the star. Basically this v equals 0 is the limiting case for v min, that is the minimum velocity which is required for this particular thing to happen. Okay, v min is the velocity with which this particle of mass small m is projected. Okay, now let me find out the coordinates of this point O. Okay, let's say this distance is x, that is the distance from the center of the smaller star till this point O is x. Definitely this distance is going to be 10 minus x. So since the gravitational field at this point O is equal to 0, I can write down gm upon x square must be equal to g into 16m upon 10 minus x square. On solving this, I'll get x equals 2a. Okay, fine. Okay, so this distance is 2a. Definitely, so this should be 10a. Okay, so this distance is 8a. Okay, fine. Now at this particular point, this particle of mass small m had some potential energy and kinetic energy. Okay, at this particular point, the particle has only potential energy, no kinetic energy, since v is equal to 0. Okay, now this whole motion, that is the motion of this particle from this point up till this point, was under the influence of conservative forces, which implies that my net mechanical energy can be conserved. Okay, so if I write down ui, that is the initial potential energy, that is going to be equal to minus g into capital M upon into small m upon 8a. Okay, fine. Minus g into 16m into small m upon 2a. Okay, fine. Yeah, it's okay, fine. So this is my initial potential energy, okay, of the particle at this point. The particle also had some kinetic energy. Okay, so the kinetic energy initial is going to be given by half into m into v min square. Okay, now u final is going to be equal to minus g into capital M into small m upon 2a minus g into 16m into small m upon 8a. Okay, so this turns out to be minus 5 g into capital M upon 2a. Okay, if I solve this ui, I'll get ui as minus 65 upon 8a into g into capital M into small m. Okay, fine. So if I conserve the total mechanical energy, I'll write ui plus half mv min square equals uf. Okay, so if I put in the value of ui and uf respectively, I get half m into v min square equals minus 5 by 2 into g capital M into small m upon 2a plus 65 by 8a into g into capital M into small m. Okay, fine. So this gives me the minimum value of v as 3 by 2 root over 5 gm upon a. Okay, so this is going to be the velocity with which the body of mass small m needs to be projected from the larger star such that it just reaches the smaller star. Okay,